Glasgow is a very ancient city. Some of the fabric of the cathedral, around which it grew, dates from the early part of the 12th century. Much of the core of the city as it stands today, however, is Victorian. Indeed, many of the more important buildings represent Victorian architecture at its best. To preserve these buildings and renew the surrounding areas of tenemental housing, which were now due for replacement, the Corporation of Glasgow produced a comprehensive development plan aimed at revitalizing the central area of the city without destroying its essential character. As an integral part of this new Glasgow, growing from the rubble of the old, an inner relief road was planned on behalf of the city by Scott Wilson Kirkpatrick and partners to provide unimpeded traffic flow around the city with easy access to the central complex which forms its commercial hub. This is a film about the construction of an elevated section of that inner relief road and the methods chosen to solve the inherent problems which arise in the building of urban viaducts. In order to provide flexibility of carriageway width, the consultants decided upon the use of precast beams of uniform length. This gave the advantage of a simple production cycle, allowing a method of construction which would permit uninterrupted traffic flow under the road spans. A feasibility study carried out by the contractor concluded that by establishing a casting yard on site, beams of a more consistent quality could be produced at a lower cost. 20 casting beds were formed with plywood soffits spanning cross timbers bolted to a concrete base. After the two lower tendons were placed on the bed, the 10mm mild steel reinforcement for the lower flange was looped around them. Each tendon, supplied by the Steel Division of British Ropes Limited, consisted of 12 Bryden 7-wire strands. These were pre-cut on site and threaded into 75mm steel sheaths. Although 26 meters in length, the internal beams were relatively narrow, their overall width at the web being 200mm. This left a space of only 120mm inside the reinforcement cage. Last to be added to the internal beams was the upper flange reinforcement. This was tied to the top of the web steel before the complex prefabricated end section was swung into position. The reinforcing steel in the U-shaped edge beams was fixed in a similar manner. Here again, the bottom tendons were laid out on the soffit first. Because of the greater quantity of steel used, however, and its more complex form, steel fixing time was almost 50% greater than that required for the internal beams. As in the case of the center beams, edge beam upper tendons were inserted manually and aligned into the correct parabolic form after steel fixing was complete. Stop-end shutters consisted of a welded steel chair-like frame with a plywood facing and leveling screws on the base. This design permitted maximum reuse, together with the necessary flexibility of end angle position to accommodate the many variations of beam end shape. Standard steel plate box outs were also provided to hold the tendon anchor cones and to form recesses for the tendon anchor plates. 4 sets of steel shutters were designed and supplied by Concrete Formwork Limited for the casting operation. 1 set was for the 5 casting beds devoted to edge beams, and 3 sets were for the 15 casting beds used for the production of the eye-shaped center beams. Before every casting operation, each pair of shutters was cleaned and oiled. During the design stage, careful consideration was given to the ease with which the shutters could be supported and maneuvered by the gantry crane. In use, The shutters were placed along the sides of the casting bed with their lower edges aligned against the soffit timbers and their ends against the stop-end chairs. Tie bolts, inserted under the soffit shutter at 1 meter centers, ensured a close fit between the soffit and side shutters throughout their entire length. Adjustment for verticality and alignment was provided by push-pull props hinged at 3-meter intervals along one side of each casting bed. During the casting of edge beams, a similar system provided a means of introducing longitudinal curvature into the shutter to produce the curved beams used in certain sections of the viaduct. Screw clamps were used to pull the top of the remaining shutter into alignment with the one which had already been fixed by the props, and U-shaped spacers were dropped into preformed holes in the shutter tops to complete the assembly prior to concreting. 2 air-powered external vibrators were attached, one to each shutter, at the point where concreting was due to start. A 0.6 cubic meter pan batching plant was set up solely for the precast works. The mix used contained a 20-millimeter washed gravel with 530 kilograms of ordinary Portland cement in each cubic meter. To give improved workability, a plasticizing agent was added, so that the concrete which it produced could be skipped direct to the full length of each casting bed. A crane track was laid to provide ample coverage of the casting area. Each beam was cast in one complete pour, commencing at one end, placing to the full height of the shutter, and proceeding continuously to the other. To give maximum effect to the vibrators attached to the side shutters, and to permit the formwork to oscillate freely as a unit, it was isolated from the casting bed by rubber pads. A poker vibrator was also used to ensure satisfactory compaction at the top of the web and in the top flange. As the operation proceeded along the beam, the 2 external vibrators were also moved to keep pace with it. A casting rate of 1 15 cubic meter internal beam in 2 hours was achieved, resulting in the production of up to 12 beams per week. A high degree of consistency in the preparation of the concrete mix was essential, since any failure to achieve the high early strength required would have seriously disrupted the 10-day production cycle. To prove that concrete strength not only met design requirements, but also allowed early stressing and transfer of beams to storage, cube tests on samples from each beam cast were carried out in the site laboratory. The cubes were required to conform to a minimum 28-day strength of 45 meganewtons per square meter. Except in special cases, pre-stressing was carried out simultaneously from each end of the beams using stressomatic hydraulic jacks. The strands of each of the 4 tendons on each internal beam were stressed to 12 tons, and those of the 6 tendons on each external beam to 16 tons. Stressing materials and equipment were supplied by Cable Covers Limited, and stressing was carried out by their subsidiary, Clough Smith Stressing Services Limited. Continuous attention to detail, like this safety barrier, helped to maintain the project's excellent safety record and win for the main contractor the British Safety Council Award for 1970. In this shot of the swaged ends of the tendons and the anchor plates, the grouting hole can be seen quite clearly. To allow mortar filling of the recesses, excess strand was trimmed off after the stressing was complete. At the end of the 10-day production cycle, each finished beam was transferred to the adjacent storage area by gantry crane. Here, curing continued, with the beams supported at carefully selected points near their ends. On 6 separate occasions during viaduct construction, a batch of beams was taken from the storage area for erection. Here, once again, the invaluable gantry crane, with its 80-ton capacity and its 165-meter long track, extending over the entire casting and storage area, made light work of the load. At the loading point, the beams were carefully lowered onto two separate bogies, positioned some 25 meters apart. To prevent instability in transit, the beams were chained down for the final stage of their journey to the erection site. The location of the pre-casting yard had been chosen so that it lay close by the viaducts. Therefore, the maximum distance which any of the beams was required to travel by transport was only about 300 meters. Maneuvering the 26-meter-long loads into a position parallel with the line of the viaduct in the rather restricted space available was greatly aided by the fact that both front and rear bogies on the specially ballasted transporter were fully steerable. The reinforced concrete pier heads and columns were designed as portal frames up to 13 meters above ground level. Each individual beam was seated on a laminated rubber bearing on the scarf joint of the pier head. The operation of beam erection was carried out under subcontract by R.G. Stewart Limited of Canvas Lang, who were also responsible for the transport of the beams from the casting area. To support the edge beams during erection, wire slings were wound around the beam adjacent to the scarf joints at each end, and the concrete in this area was protected by balk of timber from any damage which might arise as a result of abrasion under load. These huge 80-ton beams posed a particularly difficult problem in that two cranes, a 125-ton and an 80-ton, had to be used. Because of this weight and the radius at which it had to be placed, one crane was positioned at each end. Although the positioning of the beams went smoothly, it was by its very nature an operation which could never be carried out quickly. The average time required to place an edge beam from the moment it was first suspended until the moment when the slings were removed was in the order of 3/4 of an hour. Before finally placing the beam on its rubber bearings, a high-strength mortar capping was provided to ensure that the load was uniformly distributed over the bearing area. Design tolerances called for the total gap between the beam ends and the piers to be not less than 50 and not more than 100 millimeters. To achieve this, the distance between each pair of pier heads was carefully checked before the mating set of beams was cast. This procedure resulted in a consistency of fit which would have been difficult to achieve by any method involving the mass production of standard beams at a location remote from the construction site. The method of erecting the internal beams was basically similar to that for edge beams. There were, however, certain differences of detail. For example, instead of the steel slings used for the edge beams, the center beams were supported by a pair of purpose-built steel yokes during transport by a gantry crane to the loading point. The twin bogie transporter was again used, but this time positioning of the beam alongside the viaduct was made easier by the fact that all internal beams could be correctly fitted even if reversed end for end. Since each of the center beams weighed only 40 tons against the 80-ton weight of the edge beams, it was possible to lift them using only a single 125-ton crane and a double-legged sling. This simplified control of beam rotation and resulted in average erection times for center beams being considerably shorter than for edge beams, half an hour as against 3/4 of an hour. Most of the beam erection was carried out in daylight. However, in 4 special cases, which involved the placement of beams over roads which were normally subjected to continuous traffic flow during daylight hours, night shift operations were necessary. On each span of the viaduct, 5 rows of in-situ reinforced concrete diaphragms were cast between the beams, since it was intended that the 12 sets of shutters provided should be subject to continuous reuse for the duration of the contract. They were fabricated from 5mm steel and designed with a wedge-shaped center section to take account of the variations in distance between beam centers. After the diaphragm reinforcement was threaded through preformed holes in the beams, the 2 side sections were clamped into position. An important feature of the shutter design was that most of the operations involved in its erection and dismantling were capable of being undertaken from deck level, and the use of support scaffolding with its attendant cost was unnecessary. 2 rows of diaphragms were poured at one time. When the 5 making up each span were completed, the deck grid then became a structurally homogeneous unit, with the diaphragms providing the lateral restraint for the beams. At this point, the shutters for the deck soffit were placed. Again, because of the design, no support scaffolding was required. After deck reinforcement was fixed, concreting of the deck area was able to proceed. Concrete from a 0.6 cubic meter batcher was transported by telecrete and pumped through a Roadway pumping services small-bore mobile pump. At this point, too, plastizote joints were formed at each end of the deck to allow for articulation and expansion movement. Because of its long reach, high delivery rate, and the compacting effect of the hydraulic pumping action on the mix, the concrete pump was ideally suited to this purpose. Entire decks comprising 75 cubic yards of concrete were completed in 6 hours in one continuous operation. A requirement of the contract that work should proceed with a minimum of disturbance to traffic flow led to the construction of a pair of steel travelling shutters for casting the copes. These had built-in facilities for horizontal and vertical adjustment to achieve a smooth, unbroken line in the finished structure. By avoiding the use of support work, traffic was able to pass unhindered beneath while work continued above. After the deck surface was cured, the finishing phase began. First, came the laying of 2 layers of bituminous felt waterproofing on a poured bitumen seal. Thereafter, the entire sequence of operations was programmed to maintain a continuous flow of work. This period of viaduct construction also coincided with the closing stages of approach roadworks. Prior to laying of the wearing course, a protective layer of sand asphalt was put down over the waterproof membrane, and before rolling, the surface of the 40mm thick wearing course was spread with pre-coated granite chips. Erection of the welded handrail was programmed to follow the progress of cope construction to provide a safety rail during finishing operations. At the beam ends, above the location of the plastizote-filled gaps, epoxy mortar nosings were placed. After curing, special tools were used to insert a hollow rubber expansion strip into the gap, which had been set to a dimension calculated from the temperature at the time of placing. Finally, immediately before opening to traffic, road marking strips were adhered to the unchipped areas of the road surface. The completion of the Woodside Phase 2 contract, 2 months ahead of schedule, also marked the completion of the northern flank of Glasgow's inner ring road. The contract involved the construction of 7 road bridges, 2 of which were viaducts, 2 footbridges, 2 pedestrian subways, 1 kilometre of surface streets, and 1.25 kilometres of dual multi-lane motorway. Its early completion owed much to the method of on-site precast beam construction, chosen and developed by the main contractors, Balfour Beatty and Company, in association with the consulting engineer, Scott Wilson Kirkpatrick and Partners.